Very much for joining us this morning. If you don't mind, Paul, we might get started.
Yeah, sure thing.
Excellent, thank you. First of all, I'd like to acknowledge the traditional owners of the land on which this seminar takes place today, the Wurundjeri people of the Kulin Nation, and pay my respects to elders past, present and emerging. I'd also like to acknowledge the Victorian Clean Technology Fund, who are sponsoring a series of seminars being held at the college at the moment, and this is one of them. And it is my pleasure to introduce Associate Professor Paul Burke from the Australian National University's Crawford School of Public Policy, who is speaking to us today. Paul's research focuses on energy, the environment, transport, and the economies of the Asia Pacific. He has been a frequent contributor to discussions on climate policy in Australia and has published in journals including American Economic Journal, Macroeconomics, Economic Inquiry, Nature Geoscience, Nature Climate Change, and Global Environmental Change. And he's also co-leading research into policy frameworks for clean energy as part of the Energy Transition Hub here. Without further ado, I'd love to pass over to you, Paul. Thank you.
Well, thank you very much, Annabelle, and thanks everyone for coming in and tuning in as well. It's good to be being broadcast from Canberra. I'm just sitting just opposite the lake from the Parliament House, actually. So it's good to be also via the internet in Melbourne today. Today I'm talking on a really exciting topic, and that is solar panels in Australia. What I'm doing is actually presenting two papers on solar panel installations at the household level, rooftop installations. One of our papers is using postcode level data for the whole of Australia, and another paper, the second paper, is using household level data for samples of households. And these samples are around, they're more than 10,000 households across Australia. And this is work with a couple of colleagues, Rowan Best from Macquarie University in Sydney and Shuhei Nishitateno from Kwansei Gakuin University in Japan. This picture, just at the top of my first slide here, it encapsulates the energy transition that's happening in Australia that many of us know about. In the background is the Hazelwood coal-fired power station, which closed after an impressive life of 50 years operation. And in the foreground, and it's not just these houses, there are quite a few houses in the Latrobe Valley with solar panel installations like these ones. So we can see an energy transition going on in our suburbs, our communities. And in this study, we're looking at factors affecting installation rates of solar panels. In particular, we're interested in the performance of Australia's national mechanism to encourage solar panel installations, which is the Small-scale Renewable Energy Scheme. So I will be focusing on that. Just to mention also that this is a very exciting time in Victoria for household solar. And I know that there's a very big scheme down in Victoria on this. So I hope that some of the results from this study will be relevant in a very real sense in Victoria. The solar revolution. The statistics on solar are really pretty amazing these days. In 2017, in terms of capacity of installations, globally, more solar was put in than total net additions of coal plus natural gas plus nuclear power. And by net additions, what that means is new additions and also subtracting off the retirement of old plant as well. So solar and wind as well have really raced to the front of the pack in terms of new investment in capacity in the electricity sector. That first statistic does not incorporate the capacity factor, but still pretty impressive statistic. Australia is a great place to study rooftop solar. We're a world leader, very much so. More than 20% of households in Australia have rooftop solar PV. And this has come off a base of zero, of course, only a decade or two ago. So at the turn of the century, almost no one had rooftop solar PV. So here I'm not talking about solar hot water heating, but solar PV. And now more than 20% of households have it. It's quite an extraordinary change. This is more than 2 million Australian households. More than 8 gigawatts of capacity is now installed on household rooftops, well, small-scale installations. Some of these installations are on businesses as well, on business buildings also. An incredible statistic is that the total number of small-scale installations in Australia is similar to the United States, whereas of course the population of the United States is much bigger than ours. Their population is 13 times our population, but our number of small-scale installations is rather similar. So Australia really is at the forefront of markets in terms of rooftop solar installations. There's lots of good things that one could say about rooftop solar. It helps households to reduce their electricity bills. So households with the rooftop solar benefit from lower bills as a result due to being able to use the electrons generated from their panels. And at the grid level, it helps to reduce emissions by reducing the need to invest in or extend the life of fossil fuel stock. So if we have solar installations, then there's much less need to build a new coal-fired power station, for example. This graph is showing total capacity of solar PV systems in Australia, and this is just focused on small-scale systems. And my talk today will be focused on small-scale systems rather than the utility-scale installations that have started to boom in the most recent years. In this graph and in our main study here, we're using a cutoff of 100 kilowatts. It's possible to use a smaller cutoff, and most of the capacity is rather at the small end of the range from 0 to 100 kilowatts. But this graph is using a cutoff of 100 kilowatts. 24% of Australia's total solar PV capacity is in the form of installations of 100 kilowatts and below. This graph is quite an amazing story. 2008, that number is essentially 0. So this is an industry that really has just come along in the last 10 years or so, a little longer than 10 years, and it's been growing very quickly. Currently, this graph only goes to 2018. Already we're at more than 8 gigawatts. The questions that we're focused on here, number one, what are the reasons for differences in uptake of small-scale solar PV across Australian suburbs, postcodes specifically? So when we look across Australia, different areas have very different installation rates. And I'm going to show that on a couple of maps coming up. So what causes those differences? What are the factors that help to explain those differences? Number two, what effect has the Small-scale Renewable Energy Scheme had? And I'm going to explain how we analyse that question. We use geographical variation in the subsidy factor that applies for this scheme. And we try to look across postcodes when you cross from one postcode to another, and the second one has a higher subsidy. Are there more installations in that suburb? And I'll explain that as we're going into the talk. The final question here is we also drill down to household level factors explain differences in solar installation rates. And just an example is that renting households are much less likely to install solar PV than non-renters. So that's something that has already been known for a while, but we quantify it with some numbers here. For the household level analysis, if you're interested in looking it up, it is already available as a working paper on the ANU website, on the website for the Centre for Climate and Energy Policy. So that paper is available. The paper using postcode level data is currently still going through peer review, and definitely happy for any suggestions from colleagues on ways to try to improve our research. This graph is showing the small-scale solar PV installation rates across Australian postcodes. So this map is dividing Australia into postcodes, and A darker shade is a higher installation rate. Shortly, I'll show a map for Sydney as well. This map, of course, is the whole of Australia. Data are available for most postcodes. You'll see there are a couple of areas without data, but there are not many people living in those areas either. There's quite a bit of variation in solar installation rates. And it's quite interesting that some of the highest rates visible in this map anyway are in regional areas. So not necessarily just in the capital city, and that's what we're going to be finding in the study, but actually the regions outside the capital city are regions that have higher installation rates. So some suburbs shown in the darkest colour have installation rates that are really rather high. For example, in South Australia, between 32% and 74%. That's what the scale here is. I just saw the chat, but I will keep going. I believe the audio is going okay. How about for looking in at an individual suburb? An individual suburb, like an individual city. Here's the map looking at Sydney. And it's pretty interesting that the installation rates are not the highest in the inner suburbs of Sydney. They're actually higher in the suburbs which are a little further out. And you might be thinking there are quite a few reasons to explain this type of pattern. The inner city suburbs, they have more renters. They have more apartments, they have more heritage listed buildings, and so on. Whereas if you go a bit more into the suburbs, then the houses tend to be newer. They, in some areas, they tend to be larger. And also these are the mortgage built areas where people perhaps have higher tolerance for debt as well. And we're going to be looking at some of those factors in our analysis. There's a lot of range. So this table here is showing the top postcode in terms of installations for each state or territory. For example, in Queensland, the suburb, the postcode area of Olimba, the suburb of Olimba has more than 2/3 of households have solar PV. Whereas in the ACT, installation rates are lower. And our highest suburb, this is as of late 2018, our highest installation rate was down only at 20%. There's quite a lot of variation across the country in terms of the uptake of this technology. One pretty interesting summary statistic is this one. Let's look across different regions in Australia. And this graph is dividing Australia into 5 remoteness area regions. What that means is major cities, major city, an example is Melbourne. Inner regional areas, an example being the Latrobe Valley. Outer regional areas, an example being Dubbo in New South Wales. Remote areas, an example being Mount Isa in Queensland. And very remote areas, an example being Cooper Pedy. And it's pretty interesting that installation rates are actually higher in those inner regional areas, for example, the Latrobe Valley, relative to major cities. That's perhaps the most interesting takeaway from this graph. And you might be thinking that there's an explanation for everything, and we totally agree. There are lots of reasons for these differences. But if you had the prior that solar panels tend to be put in place in the suburbs with the highest incomes, then our results would run counter to that prior. So actually, as we'll see a bit later on, income is not a key explanatory variable, but some other ones are. An interesting thing also on this slide is very remote areas do have a lower installation rate. That could be because of some problems with the statistics, maybe some of the installations are being missed, but also could be due to factors such as people not knowing about the technology as much, the peer learning effects are not as strong, and also higher installation costs in very remote regions. I would like to introduce the Small-scale Renewable Energy Scheme, which is the Australian government's main scheme in this space for encouraging small-scale solar installations. Of course, if we look back through history, there have been other interventions, for example, state-based feed-in tariffs, but nationally, this has been the main game in town. What is this scheme? This scheme is a green certificate scheme. A green certificate scheme where, well, it is part of the National Renewable Energy Target. The Renewable Energy Target has been divided into two parts, the Small-scale Renewable Energy Scheme and the Large-scale Renewable Energy Target. And focusing in on this small-scale one, what it does is, if you are installing panels, then there is a certain number of certificates which are generated when you do so. And the two schemes, the small scale and the large scale scheme, are calibrated so that Australia will reach around 20% of our electricity from renewables by 2020. This scheme is, of course, coming to an end for new installations as of the end of next year. So this scheme is coming towards the end of its life, and it will be interesting to see if anything comes along to follow it at the national level. How does the scheme work? Under this scheme, certificates are provided upfront for installations of solar panels, and they're provided in proportion to the approximate number of kilowatt hours that will be generated by the system over its life. There are various rules that are applied, but the essential calculation is the one down at the bottom of the slide here. When an installation goes in, then there is a payment which is received by, in essence, by the installer, the installation company. The size of the payment is here called the effective upfront subsidy. It's equal to the product of several things. First of all, the certificate price. We do have a market for these green certificates. And so that certificate price does move around a little bit, but it's often around $35 per certificate. The size of the system, if you're installing a larger system, then you will be credited with more certificates. So that's a key point. Next one is the deeming period. The deeming period runs until 2030. So currently there are around 13 to 12 years remaining in the deeming period, whereas if you installed a couple of years ago, your deeming period would have been a longer period. Finally, the subsidy factor, and this is the one that we're really going to be utilising in this research. There is a subsidy factor which scales up the size of the subsidy that you receive if you are in a very sunny area. So if you're in an area which is very suitable for solar PV electricity generation. This subsidy factor varies by postcode. So when we use it statistically in our analysis, it's very convenient for us because we have a postcode level analysis and we can compare postcode to postcode. If you have a higher subsidy factor controlling for other things, then are you more likely to have more installations of solar PV? Who is buying these green certificates? It's a compliance market. So electricity retailers and other large consumers of wholesale electricity are required to buy the certificates. And the overall scheme is calibrated so that Australia will reach around 20% electricity from renewables by 2020. The subsidy factor is very important for the seminar today. So the subsidy factor, it varies by postcode, and there are 4 subsidy factor zones across Australia. Australia has been divided up into these 4 zones, and I'll show that shortly on a map. And these subsidy factors have been the same since the scheme was introduced. How large are the subsidies that we're talking about? They're pretty big. These are not tiny subsidies altogether. It depends on where you are in Australia, if you're in Tasmania or if you're in Northern Queensland. And it depends on the size of your system and which year you have installed your system in. For example, a household installing a 3 kilowatt system in zone 3 in 2018 would have received a subsidy of around $2,000. And that's that's a pretty reasonable subsidy as a percentage of the installation cost for a system like that. So we're talking about quite a large incentive here. This map shows the variation in subsidy factors across Australia. And let me just go through it. There are just 4 zones in Australia defined by postcode. Zone 1 is the darker shade here, and it receives the highest subsidy factor, 1.622. And an example of a location in Zone 1 is Alice Springs. So Zone 1, there are not that many people living in Zone 1. Most people live in the other zones. Zone 1 receives the highest subsidy factor. Zone 2, for example, Darwin is in Zone 2, receives a subsidy factor of 1.536. Zone 3 is, for example, including Sydney. Zone 3 has a lot of people in it, and it has one of the lower subsidy factors. But the very lowest subsidy factor, 1.185, it's a bit hard to see, but it's this lighter shade right at the base here. For example, Melbourne is in the Zone 4 area. So Melbourne receives, installations in Melbourne receive the lowest subsidy factor, and Tasmania. Of course, the design of the approach here is pretty, I mean, you can see it from the graph, the map already, it's pretty highly correlated with solar exposure, with radiation. Of course, it's not perfectly correlated though. So if you line this map up against a solar insolation map, then it's not perfectly lined up, but it looks fairly close. But yes, the rule has been to divide Australia in a pretty discrete way into 4 bins like this, 4 zones. In essence, what our econometrics is seeking to do is, for example, let's have a look at this border here between Zone 2 and Zone 3. If you cross from this suburb to this suburb, are households more likely to have a higher subsidy factor or less likely? If you're looking at a suburb in Zone 3 and then you drive into a suburb in Zone 2. As suburbs, are households in Zone 4 less likely to have installations than other suburbs? I'm not going to go too much into the statistical method, but just in a basic form, what we do is we get postcode level data. We use the solar installation rate or the total capacity of solar installations as our dependent variable. The key explanatory variable is the subsidy factor, and we take a log of that as well. We include many controls, and that's a key point. For example, we control for the solar exposure conditions faced by each suburb, and we control for some geographical variables. For example, each distribution area, electricity distribution area, we control for it with a dummy, because there are some differences in electricity prices and in historical feed-in tariff schemes that have been applied at either the distribution level or the state level. We try to control for those types of things in our analysis. And we control for economic variables, for example, the median income and the percentage of renters is another variable that we include. For those who love statistics, we also control for spatial patterns in the data that are not explained by the other variables. And why do we do this? Research from the US has shown that there's a bit of a learning effect with solar. So if we see our neighbours installing, we're more likely to install ourselves. And we try to control for that with that term, the spatial autoregressive term. We measure solar installations just for small-scale installations per household and also in terms of total capacity. And we're focused in on systems of less than 100 kilowatts. That's quite a big, 100 kilowatts is a relatively big system, but we get similar results if we use a smaller cutoff for that instead of 100 kilowatts. The advantage of the 100 kilowatt cutoff is that we have data for more years for that cutoff. And we're using installations data as of December 2018, and we have some historical data as well. What variables do we throw into our postcode level analysis? We include median income per capita. At the postcode level, we can access data on superannuation balances, which is a proxy measure of wealth. The percentage of households with a mortgage, the number of businesses per capita in the region, and so on. Geographic controls are very important, especially this first one listed here, log solar exposure. We control for that one because we want to ask the question, okay, controlling for the solar potential of the area, does the higher subsidy factor induce more installations in areas where it applies? And noting that the subsidy factor steps up in a very discrete way. We control for some other things like enhanced vegetation index. That's a measure of tree cover in each postcode. And we also control for the land area and whether an area is remote or not. There are some certain variables we use for those. We also include household characteristics among our control variables, all measured at the postcode level and as a percentage divided by 100, so as a proportion. So for example, the proportion of rental properties, the proportion of people living in apartments, the proportion of people in places that are 1 bedroom or less. And for example, we also include the proportion of people aged over 60. Are retired people more likely perhaps to have the time to go ahead and organise solar panel installations? And we try to incorporate environmental preferences by using the proportion of people who voted for the Greens or another environmentally focused party in the 2016 election. Our explanatory variables can explain most of the variation across Australia in solar panel installations at the postcode level. And just on the subsidy factor, it steps up like this: zone 1, zone 2, zone 3, zone 4. And it steps up discretely while we control for variables which are much more continuous. So we're trying to really tease out the effect of that discrete stepping up of the subsidy factor across the zones to try to work out, okay, if people were given a higher subsidy factor, would they be much more likely to install or not? We, first of all, try to estimate whether the Small-scale Renewable Energy Scheme has led to more installations. Is that a yes or a no? And then second of all, we do some calculations about the cost effectiveness of the scheme, but only in terms of one dimension, and the dimension is CO2 emissions reduction. So putting aside other benefits, let's just focus on that benefit. And we do some calculations about how useful this approach is as an approach to achieve CO2 emissions reductions. Just one other thing to note here is who gets the subsidy. It's shared between the installers and the households who put the installation in. So if there is a higher subsidy flowing, for example, by an increase in the overall subsidy factor applied to all zones, then we'd expect this to induce both a demand-side response and a supply-side response. Installers are keener to install if the subsidy factor is higher, and also households will be keener to install as well. They'll be able to share the subsidy between them in some percentage way. Where do we get data? The data on installations are from the Clean Energy Regulator, and then we get data from Australian Bureau of Statistics, Australian Electoral Commission, and quite a few other sources as well. Results. The results, first of all, for the postcode level analysis, we find that higher rooftop solar PV installation rates are to be seen in middle income areas. So it's not the highest income areas that have the highest installation rates. And this is controlling for other variables in the model. Areas with more people with mortgages, the mortgage belt areas, perhaps those areas people are happier taking on some debt. I mean, you do have to cover the capital cost of the installation. Sunnier areas, so that's good. We want to see this. Areas that are more sunny, for example, Queensland, tend to have higher installation rates than Tasmania, for example. Areas with fewer renters have much more installations. Areas with fewer apartment dwellers as well. Interestingly, areas with more retired, well, older people, specifically defined as people over 60 years old, have higher uptake rates, and that comes out in the data. Areas with more tree cover, we find, have higher rates. One might think it should be the other way around. Trees might cause shading and make people less likely to install, but maybe tree cover is also correlated with environmental preferences as well. We find that greener suburbs tend to have more installations. Outside major cities, so major cities have lower installation rates than the inner and outer regional areas. And also, if you're in a postcode neighbouring another postcode with high installation rates, you yourself are more likely to install. So there are some other spatial stories going on which are not fully captured by the variables in our model. How big are the magnitudes we're talking about here? For example, for the renting effect, if PP here means percentage point. So if there were a 10 percentage point increase in the proportion of households who are renting, so instead of having 20% of households renting moving to 30, or 30 to 40, or 40 to 50, then that is on average associated with around 1 percentage point fewer households with rooftop solar PV. So that's the magnitude of that particular effect. How about the apartment effect? If there is 10 percentage points more people in apartments, for example, instead of 20%, 30%, then that's also significantly associated with fewer installations. I mean, it's more difficult to install if you are in an apartment. And the size of that effect is 0.5 percentage points. Both of these are pretty strong and important effects that are going on. How about for the subsidy factor? So recall that the subsidy factor steps up. There are 4 subsidy zones across Australia. It steps up. Looking across Australia, we find that on average, a 1% higher subsidy factor leads to more people putting in solar panels. And the effect is about 0.2 percentage points in additional rooftop solar uptake. So for example, if the subsidy factor increases by 10%, we'd expect 2 percentage points more in terms of households with solar PV. It's quite a strong statistical effect going on. In other words, the subsidy works in terms of inducing installations. If there's a higher subsidy factor in a postcode, there are more likely to be installations in that postcode and more installations. For those who like the elasticity, and we also will be using this for our calculations, we calculate a subsidy elasticity of installations going in 2018. So this is not the stock of installations, but the flow of installations in 2018. We find that elasticity to equal 1.2. What that means is if the subsidy is increased by 10%, then we would expect the small-scale solar PV installations would increase by 12%. That's an elastic effect. And this is from looking across postcodes in terms of installations in 2018. I'm not going to show too many tables, but just one of the example tables of our results showing some of these results. Statistically, we get very strong results here. So this one is looking not at the installations in 2018, but the overall stock of installations. And for example, we can see a positive coefficient for the log subsidy factor under the small-scale renewable energy scheme. The vegetation index measure has a positive coefficient. Leafier suburbs tend to have more installations, not less. If we go down to the renting households, there's a negative result. Postcodes with more renters tend to have fewer installations. Postcodes with more apartments also have fewer installations as well. This is the result just for the flows of installations in recent years. So these are new installations that went in 2017 and in 2018. And here just showing the result for the subsidy factor. This is an elasticity because the variable is logged and both variables here are logged. What this number here, 1.15, means, that's that elasticity. Previously I said 1.2, to 2 decimal places is 1.15. What that means is that 10% higher subsidy factor induces 12% more solar capacity in kilowatts. After that, what we do is we take a step. We ask this question. If a higher subsidy factor were applied across the board, so what that means is in each of the subsidy zones, let's imagine the Australian government were to say, we want to encourage more installations. We're going to increase the generosity of the scheme by increasing the subsidy rate. This is a very relevant topic, of course, for the Victorian scheme. So the question, if the average subsidy factor was increased, subsidy factor increased across the board, how many additional panels would be installed? And then we want to ask how many tonnes of CO2 emissions avoided. You might be thinking there are quite a few steps in the calculation here. There are some assumptions, and we totally agree. The number here that comes out does depend on the assumptions. In our paper, we have a sensitivity analysis. Here we're presenting our result, but it is sensitive to some of these assumptions. The assumptions refer to a period of more than a decade into the future. So there can be good discussions about exactly which assumption is the most appropriate, and look forward to any comments. So what we use is we use that subsidy elasticity from 2018, the flow of installations in 2018 of 1.2. And what we do is we do a series of calculations. For those interested in the calculations, I'm definitely happy in Q&A to go into the details step by step, or I'm happy to send through a copy of the paper or the slides as well. I do have some slides on going through the calculations. We calculate that if this scenario applied, so if there was an increase in the average subsidy factor, the subsidy factor applied across the board, then, so in each of the zones, if they each had an increase in the subsidy factor, this would induce more panels, right? We find that positive effect in the econometrics, and that this would be able to lead to fewer emissions from the electricity system. Once we do out the calculations, we find the result would be around a cost of US $36 in subsidy per tonne CO2 emissions abated. So for every tonne of CO2 emissions abated, our calculations point to a number of about US $36 of subsidy cost. There have been some studies for the United States, which I'll mention shortly, which came to much bigger costs than this. So we find a smaller number for Australia. The calculation is subject to some assumptions. So we had to make an assumption, okay, the solar is coming into the system. What is the emissions intensity of the electricity which is displaced from that system? We went for a number here of 0.001 tonne CO2 per kilowatt hour. It would be possible to argue for a lower number there. It could be done, which would lead to a higher total cost number in our above calculation. One of our assumptions as well, and in our sensitivity analysis, we do play around with this one, is about the lifetime of the panels. Our approach has been to use 13 years, which is the deeming period for the Small-scale Renewable Energy Scheme from 2018 onwards. And how long those panels will last does depend on some things. How good will the technologies be in 10 years? Will we be replacing those panels anyway? If we use a longer period, 20 years, for example, then we can get lower numbers for that subsidy cost. And we assume an average capacity factor of the panels of 0.2. That number, one could argue slightly either way, but that's the number we use and carry out a sensitivity analysis. As I mentioned, studies for the US have tended to find higher numbers for this calculation. Why might it be lower in Australia? Australia has more favourable solar conditions than the Northeast United States. California is a different story, but then Massachusetts, for example, Australia's conditions are more favourable. Our grid is more carbon intensive. We have a lot of coal on our grid. So if you're displacing coal, then that helps to reduce emissions at a lower cost. Our subsidies have actually been lower than the US subsidies as well. And also our analysis is very up to date. We're using numbers from last year, whereas the US numbers are a bit older when panels were more expensive as well. Interestingly, US $36 per tonne CO2 is very similar to the Obama administration's cost of carbon, social cost of carbon that they calculated. The number, there's a range around it, but their central number was also US $36 per tonne CO2. As I mentioned, we also do some analysis in a different paper using household surveys. So what we do is we use two surveys from the ABS, the Survey of Income and Housing of 2015-16, and also the Household Energy Survey of 2012. The latter is quite a cool survey because it asks households, do you intend to install solar over the coming period? Whereas the first of those surveys doesn't ask that question. The surveys each have samples of more than 11,000 households. At the household level, and this paper is downloadable, as I mentioned, from the ANU website if you search for Centre for Climate and Energy Policy working papers. Households are more likely to install if we find that it's not household income that's the key thing here in terms of statistical significance. It's actually household net wealth. Households with higher net wealth are much more likely to install, controlling for other variables, except at the very highest levels of net wealth. When you're in the top 5 or 10% of the distribution, additional net wealth doesn't seem to matter. But across the distribution, higher net wealth is relevant for installation propensity. If you're not renting, you're more likely to install. If you're not in an apartment, you're more likely to install. If you're in a larger house measured by the number of bedrooms, that's how we measure it in our analysis, then you're more likely to install. If you're in a newer house, you're more likely to install as well. If you're a self-funded retiree, as measured, we measure this one by the percentage of your income that comes from a pension, including superannuation pension, then you're more likely to install. So, I mean, this probably lines up with some of your experience as well. Retirees who are relatively wealthy and that are in a house are more likely to install compared to perhaps a very young couple in an apartment, for example. If you show some environmental preference by participating in a green power scheme, you're more likely to install as well. Interestingly, for example, in the state of Victoria, if you're outside Melbourne, you're more likely to install, holding other variables constant. So there is a big city effect for our two biggest cities, Sydney and Melbourne, and also in South Australia, we can observe that as well. How about intentions to install? In the intent, we do some analysis on that. Do you intend to install solar PV? This is quite useful because this allows us to look at the effects of electricity bills and electricity prices. Why it's useful is it's hard to look at the effects of bills and prices when you've already installed, because your installation has affected your bill, the amount that you're paying to the electricity utility. So there's a bit of a reverse causality problem going on if you want to do that. But intention to install is different. That's a decision or something that you would like to do in the future. We find that households are much more likely to intend to install, and this is among the sample of households who have not installed yet. They're more likely to intend to install if their electricity bill is bigger. So there is a bit of a bill stress motivation going on here. If they've got a higher electricity bill, holding other variables constant, they're more likely to want solar. If they face higher electricity prices, calculated as electricity bill divided by quantity consumed in terms of kilowatt hours, they're more likely to want to install. If they have a mortgage, they're more likely to say that, yeah, we intend to install. Perhaps that's picking up the fact that they have ready access to credit, and perhaps they're happier to go into capital investments as well, as indicated by the fact they already have a mortgage. We don't find that income plays much of an interesting role in these household level results. Just on this, and I'm getting near the end of the presentation now, so just a couple of final points. This one I think quite nicely shows the effect of net wealth. So this is net wealth for each household by quintile. The households with the lowest net wealth are much less likely to install than the households at the richer end of the net wealth spectrum. So just a few policy implications and discussions, and then happy to turn it to questions. We find strongly in our results, and people who know much about the sector also know this already, but here we've quantified it. We find that renters and apartment dwellers, they're much less likely to install solar PV. And there are benefits from having solar PV, so some people are missing out on some of these benefits, the lower electricity bills. In future schemes, there is a potential to target subsidies in a much better way. For example, solar exposure. Solar exposure varies quite a lot across Australia, but the pretty crude approach used in this scheme just puts suburbs into 4 groups. Some suburbs in Victoria receive the same subsidy factor as some suburbs in Queensland. If you were really targeting bang for your buck, then you'd be wanting to target in a more finely tuned way. There are more costs of implementing such a system perhaps, but it's not so hard. There could be more than 4 zones. There could be a higher number of zones there. Transmission and distribution capacity. Some areas we might not want to be encouraging so much more solar, and other areas we would be. So it's possible to tailor these subsidies in ways that, from a grid planning point of view, we would like. Remote areas seem to be installing at lower rates. So for example, remote islands in Australia, Tiwi Islands, for example, perhaps there is just a call for bigger subsidies here. And net wealth, if you've got high net wealth, you're likely to install. Perhaps the role of thresholds there is important. And I know the Victorian scheme does have a threshold level of income and wealth as well for eligibility for the subsidy. Just a final point is we find that the subsidy cost for reducing emissions of the scheme, it's not too bad, but it's a little high, US $36 per tonne CO2. And just the standard point, if you're looking for the cheapest emissions reductions, then do go ahead and consider carbon pricing, because a carbon price, for example, our former carbon price of Australian $23 per tonne CO2 in its first year, it was incentivizing emissions reductions that were cheaper than $23. So those are the emissions reductions that were incentivized by the scheme. An approach like this solar scheme that we have at the moment is doing a good job in terms of rollout of rooftop solar, and Australia is a world leader, so it's really doing a good job there. In terms of emissions reductions, then it's perhaps a little on the expensive side, but it seems to be doing better than the US schemes that have been studied recently. All right, very happy to take any comments and questions. And just to mention a couple of upcoming events that are being run, a talk by Jane Hyder and also a talk by Tiffany Harrison as well. And I'm really looking forward to feedback on the talk. Thank you very much, everybody.
Thank you very much, Paul. That was an excellent presentation. Really, really fascinating. We'll take some questions now from the floor. We've got about 10 minutes, and we also have one online. I'll take one from the floor whilst I get the question ready for from Roger Dargaville online. Any questions from our attendees? Yes, just handing over to Sangeetha.
Thanks very much, Paul. I was wondering how you take account of the falling price of solar panels over time and factor that into the uptake, and also rising electricity prices driven by obviously different factors. But to what extent do they kind of eclipse the effect of the subsidy in terms of driving the uptake of solar?
Those are very good questions, and they are both very important points. But our study doesn't focus on them, and also is not affected by those issues, really. So, for example, when we're looking across the country in 2018, I mean, the reduction in the solar panel price, it's common across the whole country. So what we're doing in that postcode study is we're comparing across the postcodes. Some postcodes had a lot of installations, some not many. And we're trying to look at the effects of something else. So that something else is the subsidy factor under the Small-scale Renewable Energy Scheme, and also those other variables like the renting proportion and so on. So the two things that you mentioned there, falling price of panels, rising electricity prices, are vital factors for understanding the overall trends of things, of the installation rate over time, but are less important for understanding the answer to the questions that we were specifically exploring. And just one more point on the electricity prices. We did have a look at that in terms of intention to install. And yes, we found it to be an important factor. If electricity prices are higher, based on those household survey results, we would expect to see more people intending to install.
I'm going to see if I can pass over to Roger Dargaville. Roger, if you unmute your microphone, you should be able to ask Paul a question directly.
Can you hear me now?
G'day, Roger.
Hi, Paul. How are you going?
Good, thanks.
Great. So the question I had, and this is a little bit off the main topic, but the question about whether you paid the subsidies as the electricity was produced rather than as an upfront payment, how that might alter how the scheme works. In much the same way that the LGC scheme operates. If people got the money as the power was produced, they wouldn't get the upfront payment, so the economics would change, but it might get around issues around using this lookup table to get an approximation of how much power will be produced.
I think it's a very interesting question, and small-scale schemes elsewhere, for example, the United States, have gone for the approach that you have mentioned there. The advantage of the approach being used at the moment is it's an investment subsidy, so it encourages that initial investment. And also simplicity. I guess it is a simpler scheme rather than having to need to measure the output of all of these small schemes across the country. And simple is good and preferable. So I think that really is the main thing going for the current approach. And it's quite a big thing going for it. This is a simple approach. You get the subsidy up front. And once you have the panels in place, you still have the incentive to use them and to generate the electricity. So not being incentivized directly via a subsidy for that flow of generation isn't such a problem, because you still do have an incentive to use them really as much as possible. So that's my summary, but I'd like to have a chat sometime if you have other thoughts about that as well, Roger. Thanks.
It's also possibly interesting because solar panels sometimes don't always work. We've seen voltage issues dropping inverters out. So some people are getting subsidies for PV systems that actually aren't producing as much power as you might expect.
I think that's a very good point. I would love to see some data on that. I think it's a very good point. And certainly for large-scale systems, you would not want to go for the type of approach here, and we haven't done that. But yeah, I think as an analytical question, that's a great one for some analysis. Roger, you might be able to mention if anyone has done a report on that already.
Naomi Stringer at UNSW has done a bit in that space, but yeah. I'll hand back to the rest of the audience to ask questions.
Thanks, Roger.
Thanks, Roger. We have one from our audience member here, Robert McLean, and then I'm also going to see if Peter Burke would like to ask his question online. Go for it, Robert.
Well, thanks, Paul. Paul, have you any examples of large buildings putting PV on their roofs and then selling sections of that to renters?
Well, there are lots of models for the renting market, and these are very much still developing. So I don't know specifically about examples of that, but in our data, we're not able to distinguish whether that has ever happened, but we're only able to measure whether those renters physically have panels on their roofs. But I think that the space that you're talking about is a vital one moving forward, how to help develop these markets in solar-powered electrons, electrons from solar power in a way that renters can have strong participation, and apartment dwellers as well. India is a country that's making quite a bit of progress on this, on different models for solar power in urban settings where many people live in apartment buildings. Roger or someone else might like to jump in and help answer the question. But for our study, yeah, we're just looking at actual installations by renters themselves.
Roger, if you don't mind, we might take a question from the webinar, and then we've got another couple on the floor, and I'm just conscious of time.
That's fine.
Thanks, Roger. Peter Burke asks, how does the existing grid and its distribution affect the installation rates and size?
Well, the key thing, if we're just focusing in on this scheme, the small-scale renewable energy scheme, is that it's not calibrated for the grid and for optimizing the installations and where they go. So you get more subsidy if you're in a sunnier area based on those 4 zones, but it's not calibrated based on other dimensions like ideal locations for the transmission and distribution system. So going forward, if those factors want to be considered important, then some reforms to this type of approach would be needed. Yeah.
Thank you. And 2 from the floor, 1 from Malta.
Thank you, Malta 9000. Thank you, Paul. Great presentation. What's your take on the Victorian solar rebate for renters, where like renters pay for amount of time and the landlords get also part of the subsidy? Have you had a look at this, and what's your take on it? I think it only starts at 1st of July or something, 1st of June.
I haven't had a look at this, so I'm not going to come in with a big comment on that one. But it is very interesting to see a key state focusing in on this issue of renters, because it is obviously a big reason why lots of people aren't benefiting from this transition. And it's not just solar panels, it's batteries as well. But yes, I think I'd need to look more closely at the Victorian one before making a comment there.
A question up the back. Could you please introduce yourself?
Is it okay now? Yeah. Hi, Paul. Jordan Panayotov, Independent Center for Analysis and Research of Economies. We did work on this since 2010, when the Global Working Group on Climate Change and Health has been established in Geneva. And I want to ask something regarding your last slide, which was policy implications. So we didn't hear anything about recommendations on how to improve policies in order to increase not only the uptake of solar systems, but also in order to improve fairness of the policies, because everybody agrees that renters, the current policies are actually unfair in relation to renters. So this is the question. What recommendations would you make in order to change policies in the way they improve fairness, so that renters will be not 3 times losers? By 3 times losers, they are worse off compared to household owners. They are losers because they do not get the subsidy initially, and they are losers because they are fully exposed to the new higher electricity prices, which producers of electricity do in order to keep up the profit, because wealthier households put solars and they are less exposed to the new higher prices. And this is described in a paper, the role of average health status, health inequalities matrix, for assessing impacts on population health in all policies approach. So this is the question: what recommendations for improving fairness of the policies?
Well, I think it's a very important issue. And we do have another paper, which we call the renter's curse. We try to control for many variables, and then we just look at whether renting households pay more for their electricity bills than non-renters. And we find the answer is yes, using Australian data. So there is an issue there. One approach is to better means test any subsidies which are given out. If subsidies are flowing to households with millions of dollars of assets already, then I think it's fair to ask, why would this subsidy be needed for them from an equity point of view? Those households might well put in panels anyway, so it's not so efficient to do so either. I think at the end of the day, interventions can be better targeted. That's one answer. If there's any subsidy involved, it could be better targeted at low-income households and other disadvantaged households on this topic, like renters. And also, perhaps there are some potential reforms out there to just make help the market to work more smoothly as well. For example, renters, one thing about renting is you can see if there are solar panels on your roof. So it's not a hidden problem, a hidden asset. We can see it. But sometimes perhaps there needs to be some way of better sharing the benefits of them with the renters so that they capture fully the benefits in terms of electricity price reductions. I think it's an important area for further study. We haven't fully done a full study on that, but I think I'm looking forward to seeing a good report on this, and it's a crucial issue going forward.
Thank you, Paul. Please put your hands together for an excellent presentation. Thank you, Paul.
Thanks very much, everyone. Thanks for coming along.
And if you do have any further questions, Paul's details are on the next slide. Just there, Paul's email address. You can also find him obviously via the ANU website. And finally, just some upcoming seminars at the college. Next Wednesday, the 29th of May at 11 AM, we have Jane Hyder from CORE's Chambers Westgarth talking about aggregation in renewable energy here at the college, and that's another VCTF sponsored seminar. And on Monday, the 3rd of June, we have Tiffany Harrison, Executive Officer of Climate Emergency Darebin, leading a panel with Luke Taylor and Philip Sutton on climate emergency, the role of local government in tackling climate change. And that's co-hosted with BZE and will be held over at the Fritz Lowe Theatre in the McCoy building over on Elgin Street at 6:30 PM. Thank you very much for joining us today.
See you later.